All right, here we go. We are working on practice file 3-2. And for these, you need to think back to the tension demos that we did yesterday. So for each of these, you want to make sure that you are, in fact, drawing a free body diagram to help you sort of think about what's going on here. This is a habit you want to get into going forward. Your free body diagrams are going to be part of your quizzes and your tests when you get assessed later on. So please be able to draw these. So we're going to start with Nellie Newton. And again, as with all free body diagrams, start with a box. There's Nellie. And we know that according to the problem here, she has a weight of 300 newtons, meaning her force of gravity is 300 newtons. Okay, now, we also know from reading this that her net force must be 0 on her. So if her F net is going to be 0, well, we see in this case that there is a 1 support holding her up. So we have tension, 1 source of tension, Ft, supporting her. So in this case, the tension must be equal and opposite to cancel out and give us a net force of 0 newtons. So in this case, the tension in the scale is 300 newtons. Okay, number 2. Now we have 2 scales lined up. So again, we'll go ahead, draw in the free body diagram. There's Nellie, box for Nellie. We know that she still has a weight of 300 newtons. And in this case, again, we see there is only 1 source of tension. And if you'll recall the demo yesterday, okay, it does not matter how long that source of tension is. It could be a really, really long rope, could be a very, very short piece of string. It doesn't really matter. Okay, the tension throughout that support is going to be the same. So even though there's 2 scales, okay, both of those scales are going to read the same thing. They're still going to read 300 newtons. Okay, so the answers there for both were 300 newtons. And again, she's in equilibrium. We see that the tension pulling up is counteracted by her weight pulling down. And again, she is at rest in equilibrium. All right, next one. She's now on a trapeze, and now what we see here is we do have 2 sources of tension. Okay, now she is distributed in the center of both of those sources of tension. So if we go ahead and we draw our free body diagram, the Earth is still pulling Nellie down with 300 newtons of force. Okay, and in this case, she now has 2 sources of tension. So when I go to draw these, I want to draw them to scale. Okay, so that just means that this weight is going to be distributed evenly here and here. So it's going to supply in each source of tension half of the force to support the weight. So, of course, all we're going to do here is we're going to take our weight, 300 newtons, and we're going to divide it by 2, and we will get 150 newtons of tension in each support. So Ft is 150, and Ft is 150 in both supports. Okay, so keep going here. Now we have 3 sources of tension. Again, here's Nellie Newton still hanging from all 3 supports, and clearly we can see there's 1, 2, 3 supports holding her up. So again, she's in the center, so her weight will be, again, pulling her down with 300 newtons. But now we have 1, 2, 3 sources of tension holding her up. And again, notice what I did there. I drew them to scale. They are all the same length, and they are all about 1/3, right, of our weight vector pointing down. So all we're going to do here is take our 3 sources of tension and divide the 300 newtons of weight by 3, and we should get 100 newtons in each supports. All right, and now keep going here. So now we have Nellie holding onto the edge of a cliff and holding onto a rope. So if you think about it, her arm here is pulling up on one part, okay, and then her arm here is connected to this source here pulling up on another part. So if we think about this, there are actually 2 supports holding her, right? We've got the arm here, and we've got the arm here. There are 2 sources of tension. So if we draw this picture, again, here's Nellie Newton. Here's her weight pulling down, which is 300 newtons, and now we've got 2 sources of tension pulling her up. And in each case, we're going to take 300 newtons, divide it by 2, because her weight is distributed evenly over those two sources of tension. So we should get 150 newtons read in the scale to the right. All right. Next one here. Again, we see that we've got this rope contraption here, sort of hanging. There's the rope, there's the rope, there's the rope, and it's connected to the scale, which is connected to one ring there. So this whole thing here is just one giant support. So really what we have here, folks, is we have Nellie Newton, Earth pulls her down, and then there is the one ring supplying the tension that pulls her up. So of course, if her weight is 300 newtons, then the tension will also be in that one single support, 300 newtons. And equilibrium for all of these cases, she is completely at rest. All right. So now we've got a different scenario here. We've got a painter standing on a support, a board rather, and then it is supported by two sources of tension. Okay, and we are told that in this case, the painter is in the center, okay, and the tension to the left is 500, and the tension to the right is unknown. Well, in this case, okay, we see that we've got the Earth pulling our painter down, and then we're going to have two sources of tension pulling him up, Ft and Ft. And of course, these two sources of tension here, right, must add up to give us our weight here. We also know that because the painter is in the center, okay, those two sources of tension must be equal to one another. So if this source of tension to the left is known to be 500, the tension to the right must also be 500 newtons. Now, if both sources of tension are 500 newtons, right, 500 plus 500, pulling up, well, then that just tells us that the weight that cancels out pulling down must be 1,000 newtons. So Burl weighs 1,000 newtons. Okay, and again, we are still in equilibrium. Our two sources of tension cancel out with our one source of weight. Next example, Burl the painter starts distributing his weight to the right. Okay, so what we see here is that this scale decreases to 170, okay, but remember, he is not falling here, so he still is in equilibrium. So this scale here must supply enough tension to still cancel out with his weight. So what we see is his weight is still pulling down with 1,000 newtons. We've got a very small source of tension here that is 170, and we're going to have a much bigger one over here that, well, if you take 1,000 newtons and you subtract 170 newtons, you should get 830 newtons for your answer here. Again, our upward forces must cancel with our downward forces to keep our painter in equilibrium. Now he's hanging off the edge here to the point where we see that the scale to the right is reading 0. So there is no pull on the scale to the left, pardon me. So he is all the way over here on the right. So if all of his weight is distributed to this one source of tension on the right, well, we have one pull down, and we're going to have one source of tension pulling up. And of course, if his weight is 1,000 newtons, then the tension in the scale must also be 1,000 newtons in order to cancel out. Now, the last example here, we've got a rock hanging at rest from a single string. Only two forces are acting on it, the upward tension T, Ft of the string, and the downward pull of gravity, Fg. The forces are equal in magnitude and opposite in direction. So the net force in the rock is what? Well, again, they're telling us that the forces are equal in magnitude and opposite in direction. So that just means that Ft minus Fg equals 0. They do, in fact, cancel one another out. Our rock is in equilibrium. So now we've got the same deal going on. The rock is now suspended by two strings. Tension in each string acts in a direction along the string. We'll show tension of the left string by vector A and tension in the right string by vector B. The result of A and B is found by the parallelogram rule and is shown in the dashed vector. Note that it has the same magnitude as Fg. So the net force on the rock is what? So again, they're telling us that basically A plus B equals Ft. Okay, so this should look a lot like your table lab, your knot lab, where the knot was not moving, right? So we have one vector here, Fg, that cancels with the sum of AB. So again, in this case, our net force is still going to be 0, because everything cancels out. So now, what we've got here is we've got our strings are now at unequal angles. The result, A plus B, is still equal and opposite to F, and is chosen by the dash vector. Construct the appropriate parallelogram to produce this result and show the relative magnitudes of A and B. So these strings that you see here, these are not the actual length of A and B. We're just saying that these are the directions. So in order to get A plus B equal, right, to this vector here, okay, well, A I'm going to do in blue. Okay, A has to travel along this line, and A has to go up to the edge of the box. Okay, and B is going to travel along this line, and B has to also go to the edge of the box. So now, if we look at these, we go ahead and do our parallelogram method here. And we transfer B over. There's my B. There you go. We've got A plus B makes, right, our F net vector. We do the same thing here for A. Whoops. Do the same thing for A. We can transfer it over. Right, we'll bring it over here, and again we see that A plus B still makes that tension vector pointing up. So now the million-dollar question is, how do A and B compare to each other? Well, let's look. Here's, if we look at B plus A, whoops, let's move them out of the way here. Let's see. All right, we take these two things and we can kind of take a look at the overall difference in the lengths. Well, it should be pretty clear here, right, that this is vector B, right, and then this over here is vector A. We should see that pretty clearly A is much longer than B. Okay, and again, the length of a vector tells us the magnitude. So A is much longer. That tells us that the tension in A is greater than the tension in B. Right, A is pulling harder. Okay, and again, the reason for that is because A is pulling up more than B. A has more of the weight distributed to it than B does. So A has greater tension. Okay, so now in this example here, we're supposed to do the same thing. We're supposed to figure out which vector has more tension in it. Again, A and B, those lines there, the black lines, only tell us the direction, not the length. So what you got to imagine here, right, is that A goes along, I'm going to do A in blue. A goes along this line till it gets to the edge here of, whoops, to the edge of the red vector. So there's my A. Something like that sort of, right? Or let me backtrack that a little bit. It wants to go about here. There we go. There's A. Okay, and then B is going to go along the edge here until you get to the edge of the red line there. So now if we add A plus B, right, we see that A plus B adds up to give us our red. So now again, compare the two. Right, you can clearly see that vector B here is much longer than A, so the tension is greater in vector B. And again, why is that? It's the exact same reason as the previous example, right? B vector is much longer than the A vector, so its magnitude is greater that we see here. And the reason for that in real life is, of course, that B is supporting more of the weight of that rock. It is pulling upwards, it's pulling more vertically. Okay, and then for the last part, we're supposed to go ahead and construct vectors A and B for each case. First, draw a vector Fg, and then the parallelogram that is equal and opposite vector A plus B as the diagonal, and then find the approximate magnitudes of A and B. So basically all we're doing here, guys, is you're going to say that this rock has some vector Fg, and we're going to use that same vector for all of these. So it's going to be Fg every single time. So I'm just going to take my Fg here, I'm going to copy, I'm going to use it here every single time for my rock. So I'm going to paste it in for all of these, something like that. There we go. Paste it in here for this one as well. Okay, now in each case here, A and B on the black lines is indicated, the direction of A and B is indicated by the black lines, not the length. So the idea here is that, well, we need to create a vector, that is equal and opposite. A plus B must create a vector that is equal and opposite to FG. So the way we're going to do that, right, is we're going to create another vector that is equal and opposite to FG, which basically looks like that. Okay, so there's my FG. A plus B must equal that red one. A plus B must equal this red one, and A plus B must equal this red one. So basically what I'm going to do here, guys, is I'm going to say, okay, well, B, again, must go up to the edge of the red one. A must go to the edge of the red one. So there's A plus B. Right? A plus B gives us the red one. In this case, again, we want A plus B to equal the red one. So again, my B is going to go about there, and my A is going to go about there. Oops. So we add them up. A plus B, there we go, makes the red one. Okay. And then we do the same thing for this one over here, this example. This one gets pretty crazy over here. So again, we're going to take our A, and our A is going to go like all the way out to like there. And our B is going to go all the way out to like here, something like that. And again, if we add these two up, again, it's not perfect. I'm having a hard time there kind of getting them perfect, but something like that, approximately. Okay, so the A plus B also makes the red one here. So what we see in these cases is how do A and B compare for each example? Well, if we look at them, right, in this case, the very first example, A and B are very short. Okay, in this example, A and B are a little bit longer. And in this example, A and B are the longest. Okay, so what's happening here is what you'll notice is here, right, A and B are pulling less horizontally. So they're not pulling out to the sides as much in this example here. So what we see is the overall force is less. Over here, A and B are pulling up, but they're also pulling really, really hard out to the sides. So the forces in A and B in this final example are the absolute biggest. Okay, so the more you pull out to the side, the more force you add to your tensions. The more you're just pulling upwards, you're only supporting the weight. Kind of tricky, but there is your answer. And that is it for workbook or practice file 3.2. Thanks for watching.